Theorem 21 says this: if the opposite sides of a quadrilateral are equal, then that quadrilateral is a parallelogram. This is the converse of Theorem 19, which said that the opposite sides of a parallelogram are equal. So we're now going to flip it on its head and say the opposite. We're going to say if the opposite sides are equal, then it's a parallelogram. All right, so we're given a quadrilateral ABCD where AB equals CD and AD equals CB. First thing we're going to do after we have already obviously stated our given, we're going to draw an auxiliary line to help us prove this. Draw AC. And we can say that because 2 points determine a straight line. So let's draw AC. Okay. Now we can say something about AC. Pretty simple here. AC equals CA because of identity. Number 4, we can now say, let me make my mark here. We can now say triangle ABC is congruent to triangle CDA by side, side, side. Number 5, let's label some angles here. I'm going to label this angle 1, this angle 2. Let me zoom in a little bit. This is going to be angle 3. This is going to be angle 4. All right, so I can say that angle 1 equals angle 2, and that angle 3 equals angle 4. It's the same reason, but we have to be careful that we are looking at the right lines to be able to say this. We have parallel lines here because we can't say they're equal because of parallel lines. We've said that the triangles are congruent. We've said that this triangle is congruent to this triangle, and so we can say this because of CPCTE. I started getting ahead of myself, but we can't state that they're alternate interior angles of parallel lines because that's what we're really trying to prove. If these opposite sides are parallel to each other, then this is a parallelogram, and that's what we're about to say. But we can say that this equals to that, it is equal to that, because they're corresponding parts of two different triangles that are congruent to each other. And the same thing about these two triangles, or two angles. Oh man, I'm sorry. All right, number 6. We can say that AB is parallel to DC, and that AD is parallel to BC. And now we can say this: if alternate interior angles of two lines, and I'll even say two straight lines are equal, then those lines are parallel. Pretty truncated and abbreviated reason there, but this is what I'm saying. If these two lines are pretty much cut by a transversal, that's understood pretty much by my statement here, and they form alternate interior angles between those two lines. If those two alternate interior angles are equal to each other, that makes these lines parallel to each other. Or that doesn't necessarily make them, it means that they are parallel though, because that's an attribute of parallel lines. And with these parallel lines here, or lines that we are just stated to be parallel, if they are cut by a transversal and they form alternate interior angles that are equal to each other, that does mean that they are parallel. And so if the opposite sides of this quadrilateral are parallel, that means that this quadrilateral is a parallelogram. ABCD is a parallelogram. Definition of parallelogram. All right, there it is. Theorem 21, if the opposite sides of a quadrilateral are equal, it is a parallelogram.